Look at another example here. We're going to see the line integral over c of FDR for f of xy is the same one we did in our previous example, y cubed plus 1 plus 3xy squared plus 1. And then we're this time doing it along a slightly different curve. So we're starting at 1, 0. We're following the semicircular arc back to -1, 0, and then the straight line across the x-axis back to 1, 0. So essentially C is piecewise smooth and it both starts and ends at 1, 0. So what I want to do is think about this one with that fundamental theorem of line integrals, and we're going to see kind of an important result coming out of this example. So think about the fundamental theorem of line integrals. So that one has to do with whether or not f is conservative. So let's just reconfirm that. We did it in the past video too, but we'll do it one more time here. So let's say check f is conservative. So we take that partial of m with respect to y, which is the partial with respect to y of y cubed plus 1, which ends up as 3y squared, and the partial of n with respect to x, which is the partial with respect to x of 3xy squared plus 1, which will also be 3y squared. So since those are equal, f is conservative. So what that means is the fundamental theorem of line integrals applies. Now remember what that fundamental theorem of line integrals says. It says that what we can do is we can evaluate the line integral of f dr by instead taking that potential function and evaluating it at x of b, y of b, and subtracting the potential function of x of a, y of a. Now in the previous examples we've done, we've actually looked for that function little f, that potential function that we have for capital F, and then evaluated it at our initial point and terminal point. But notice here, x of b, y of b, so that's the terminal point. Well, we ended our curve C at 1, 0, but we also have that our initial point, x of a and y of a, is 1, 0. So what we're going to have up top is this line integral is going to be f of 1, 0 minus f of 1, 0. So in a way, it really doesn't even matter what the function f is, because either way, I'm evaluating it at 1, 0, which will give me some output, and then subtracting off that same output. So this is going to be 0. I don't even need to find what that potential function is. Now, in a way, this also sort of makes sense, because remember, another property we said when we have conservative is this idea of path independence. So when we scroll back up and look at this picture up top, the first part of this curve, when I do sort of that semicircle arc from 1, 0 over to -1, 1, well, I could have chosen any path to do that, including, if I had wanted to, I could have taken the path that just went straight along the x-axis in this direction, so moving towards the left, and then from that point just then taken a next integral and done the exact same line integral, but instead going towards the right. And we get this idea that, well, they would cancel each other out, right? We do one motion and then we do the exact opposite, and they'll end up canceling each other out. Whereas the other way to see it is from this fundamental theorem of line integrals. We're literally going to plug in the same point as my initial point and terminal point. So therefore, no matter what that potential function is, we're just going to end up canceling out to a 0. So this gives us a really important theorem that we can write down. That's a very useful theorem. It says that f is conservative if and only if the line integral over c of f dr equals 0 for every closed curve C. Which, being a closed curve C, would mean that idea of C starts and ends at the same point. So we just saw this in one of the directions, right? If f is conservative, then that closed curve line integral will equal 0, but it turns out that it's actually true in the other direction as well. If you could argue that this line integral is 0 for every possible closed curve, which is a fairly difficult thing to show because there's infinitely many possibilities. But if it is true, that is the only way that f is conservative. So if you can confirm that a function is conservative and you're trying to evaluate a line integral on a closed curve, then you're going to end up being able to just immediately conclude that that line integral is 0. And the reasoning is directly from that example that we just finished up above.